Rhodium, it turns out, also likes hydrogen. It is a very remarkable element. Today I'll be talking to you about challenges towards GX based on basic nanochemistry. One important keyword in basic nanochemistry is something called a cluster. One way to think about clusters is a bulk substance miniaturized to the extreme. One angle of our research is to make big clusters smaller and perhaps discover new properties that didn't exist before. Another is to create clusters of different sizes and study whether certain sizes show very high reactivity or some other interesting behavior. Today I'll be discussing rhodium, which is a type of metallic element. When clusters are made from a metallic element, they are called metal clusters. Metal clusters are closely tied to catalysis. The target for this particular study was to observe the interaction and reaction between metal clusters and small molecules. One particularly important reaction is the reduction of nitric oxide, NO, by rhodium. Aren't most cars going to be electric in the future anyway? There might not even be cars that release exhaust gases, so what's the future of something like an NO reduction catalyst? Some of you who are young may be thinking this. But there's actually another miracle we have to consider here. Rhodium, it turns out, also likes hydrogen. How rhodium adsorbs hydrogen, transports it, and releases it where needed is important. What we see here is that for vanadium and cobalt, we have to raise the temperature to around 800 or 600 degrees Celsius before the hydrogen desorbs. However, rhodium, in that sense, is a very remarkable element, as all of its hydrogen actually desorbs at around 400 kelvins, or 100 degrees Celsius. What we found was that rhodium clusters, compared to other elements, both adsorbs more hydrogen atoms and has a remarkably low desorption temperature. What we're now aiming to do is figure out how to reflect that in the creation of new things.